Hello, my name is Tracy Brenner, and I'm a technical advisor for IHS Piper. Thank you for joining me today. Today we're going to talk about using IHS Piper to cut costs through gathering system analysis. In times of low commodity prices, it is important to have a tool that allows you to quickly identify any existing bottlenecks and provide an interface to allow you to run optimization scenarios or decommissioning scenarios. During this presentation, I will demonstrate the capabilities of IHS Piper to help you identify areas to investigate and test cost-cutting scenarios, including decommissioning and optimization. To give you a brief outline of where we're going to go today, we're going to discuss what IHS Piper is, how to build a gathering system model. We'll talk about a base case gathering system. So this is a scenario that exists as it is in the field currently with no changes. Then we're going to review some multiple scenarios of different ways to cut costs. And finally, we're going to use economics and check the gas rates being delivered in each of those scenarios in order to compare them. IHS Piper is an integrated three-phase hydrocarbon gathering system asset modeling tool. All data can be spatially aware, that is, using a geographic information system or GIS. And when in GIS mode, each facility is assigned a fixed geographic location. All the spatial data I will show you today was obtained from Eden. For those of you who may not be familiar, Eden is an IHS web-based energy database. It is spatially aware and contains exploration and production data, basin information, and midstream content for over 250 countries. You can create searches on multiple criteria, export data in the form of reports, create maps, and export spatial data, like shapefiles. All of this is done through a standard web browser. For today's project, I searched by country, in this case Italy, production phase projects with gas, and then used a spatial search on the map to limit the dataset geographically. The data exported from Eden to create the model I'm showing you later included shapefiles and a satellite image, which we'll discuss in more detail. Your entire surface network can be modeled, including compressors, pumps, amine units, and separators. Operational curves for compressors and pumps may also be entered. Fuel gas usage can be considered, as can equipment losses. Deliverability models may also be used, including IHS Harmony rate transient analysis and coal bed methane models, RTA and CBM, as well as gas inflow performance relationships like wellhead test or sand face. Gas, oil, and water can be included in models, as can temperature effects and equations of state. Pressure loss calculations include both frictional and hydrostatic components and factor in temperature and phase change effects if those options are selected. There are many diagnostic maps in IHS Piper that facilitate identification of operational issues like liquid holdup or hot taps, opportunities to cut costs, and opportunities to optimize production. Today we are going to talk about modeling cost-cutting measures, including their impact on field deliverability, revenues, and net present value. While cutting costs is one way to maintain profitability during low commodity prices, another is to increase revenues more than the expenditures required to achieve those increased revenues. Some of the scenarios we review today will also demonstrate increased revenue. The first thing we're going to do is look at the base case. The base case for the gathering system is the scenario where nothing has been changed. This is as the system exists in the field today. All the spatial data in this model was brought in from IHS Eden, as I mentioned earlier. It's a gas gathering system with a delivery point, multiple offtakes, about 130 wells, and 5 compressors. If we use the base case model to run forecasts, it's going to forecast gas rates and pressures that would be the case if no system changes were made. Switching over to Piper now, let's take a look at this base case. This is the GIS interface for Piper. Right now, you may notice that we have a satellite image showing on the screen. This image was actually taken from IHS Eden. If I zoom out for a moment, you'll notice that geographically we are located in Italy. If we want to return to that image, I'm simply going to go to the image layer area. And what we're looking at is the topography really of the area of interest that we're going to build our gathering system on. You'll notice there are some dark brown dots here. Those indicate wells. And we're able to see some lakes, streams, and the coastline here. How did we get this image into Piper? What you need to do is simply provide locations where you know the latitude and longitude and pin the image to that location on the surface. And this is the result. So while you'll notice in this side property manager we have the satellite image turned on, we do also have a number of shapefiles available. If I click on the city areas in green, I'm just going to move the image up. You'll notice here that this is the footprint of a city sitting on the coastline. And that shapefile was brought in from Eden as well. If I turn on the fields, you'll notice there are some light yellow polygons, and those indicate producing fields in the area. There's also a gas pipeline file. This is also a shapefile from Eden, and they're showing here in gray. So these are all the gas pipelines running in this region. You'll also notice a well point file. These gray circles surrounding the brown dots are the location of wells brought in using a shapefile from Eden. We've also brought in lakes and rivers to assist us with orienting ourselves with the regional geography. Now, if you aren't familiar with shapefile, they are geographically aware files that contain attribute data. If I right-click on this pipeline file and open the attribute table within it, you'll notice that there are names for each of these pipes, but more importantly, we also have lengths and diameters. So when we import a shapefile, we're able to bring that data into Piper as well, which facilitates building a gathering system quickly and easily. You'll also note that if I open the same attributes for the well shapefile, we have the well name along with many other attributes, and we're able to bring some of these attributes in to Piper for building our model. I'm going to turn off the satellite image right now. And what we're going to do is convert these gas pipelines into pipe links within Piper. There is a conversion process in Piper. It's very easy to follow. And the result is a series of links representing pipelines in the software. And you'll notice that each of them is a different color. And this color is telling you the diameter of each of those pipe links. If you needed to see the legend for that, you can simply drop the link colors on here. So you'll notice that purple pipe links are between 12.5 to 16 inches in diameter, and this legend can be customized. If we go into the gathering system editor, you'll notice that for each of these pipelines, it has an internal diameter as well as a pipe length that was brought in with the shapefile. We've also converted the wells into facilities using the shapefile. Notice each of these red icons with the rays coming out of them. Each of those represents a wellhead test well. And you may notice that there are other facilities on screen that you might not recognize. The small red squares are nodes, so these are locations on the surface where currently pipe links are joining, and they can also represent any other type of facility like a compressor or an inlet delivery point. What you'll see here in blue are multiple offtakes within the system. Some of them are servicing agricultural areas, and some are servicing cities or towns. You'll also note there's a delivery point, I'm just going to zoom in here, as well as a gas separator in this location. You may notice that there's a field just close offshore here as well. The deliverability for each of these wells has already been set for the model, and we're able to view that through the well editor. Notice that the well names came in from the shapefile. Each is attached to a node. Each well's deliverability has been entered within the well editor. And note that each of them has a reservoir attached, shown here. Now that our gathering system is built using spatially aware data, it's time to start looking at opportunities for cost cutting. The first way to do this is to investigate any operational issues that may exist in your gathering system. And there are many diagnostic tools within Piper to help you localize any operational issues and uncover what might be causing them. Some of those diagnostic tools include the pipeline pressure loss map, gas velocity map, and frictional pressure loss map. Operational issues cost money. Identification and mitigation can reduce costs or be cost neutral and improve revenues. We recommend that models be calibrated to ensure that the model in Piper matches the field, and we do this by using measured data and comparing it to values calculated within the software. Specifically, we compare measured pressures against calculated pressures. The process of calibration frequently uncovers operational issues that may not be known to the operator. As a result, corrective action can be taken to fix or mitigate operational issues, which results in a more efficient and more economic gathering system. If we switch back to our model, I'm just going to turn off the rest of these shapefiles. And I'm going to run a forecast just to calculate rates and pressures in the model as it currently sits. Now, I mentioned that there was a pipeline pressure loss calibration map that could help us identify operational issues. What I'm going to do is switch that on here. We call this a bubble map, and you'll notice that around each well, there's a circle in different colors, and those colors are outlined in the legend here to the side. So you can see that anything colored in green is plus or minus 13.8 kPa pressure between what was calculated in the software and what was measured at the well site. Now notice that most of the wells are showing in green. This means that we have a good model match. What's being calculated within the software closely matches what we're measuring in the field. However, when we look in this area, which is the Turi field, you'll notice that there are quite dark red bubbles around the wells. And the legend tells us that that shows a pressure discrepancy of 55 or more kPa between what's calculated by the software and what we measured in the field. And as an operator, you'd want to go in and have a closer look at this and see if you could identify the reason for that. One way to further investigate what may be happening in this region of the gathering system is to have a look at the frictional pressure loss map. And in order to see that, I'm just going to turn off the links. So you'll notice that all the pipe links have been colored this pale purple color. And if we look at the legend for the frictional pressure loss map, you'll see that we have very low frictional pressure loss within all of these lines. So in fact, this entire gathering system isn't demonstrating a lot of frictional pressure loss. With that in mind, we wouldn't expect this discrepancy to be a result of frictional pressure loss. So what else might we think about? We could also check the gas velocity map. And again, gas velocities are very low in this system. If we look at the legend here, they're less than 1.5 meters per second in this case. So it's really not pointing towards a frictional issue like a hot tap or a partially closed valve. In this example, what could very likely be happening is liquid building up. If we went to the field and measured pressures at this location and found that, let's say there was a 75 kPa pressure loss at this site and it was due to liquids holding up, what we could do is model that as a fixed pressure loss. And so what I'm going to do is convert this into a fixed pressure loss. and then I'm going to set the value to be 75 kPa. And now I'm going to update the forecast. So we're going to run the calculations again for pressures and rates. And notice that this Turi field is now also showing in green, so it's well calibrated. We've discovered an operational issue. In this location we had liquids holding up. We might want to take some mitigating action in order to correct that. And if we do, then the model is going to do a much better job of predicting what's going to happen in the future. If in fact this turned out to be a frictional pressure loss, like a hot tap, we would instead turn this into a variable pressure loss, which would reflect a frictional issue operationally in the system. We would now consider this model well calibrated. I'm now going to switch to a completed model, fully calibrated, precisely the same system that we were just looking at. Notice the satellite image is showing. We have all of our pipe links, which are color-coded based on their diameter. Facilities like delivery points, offtakes, and separators are showing, as well as all of our wells. You may also notice some facility annotations. I'm just going to turn off the satellite image to make those easier to see. In the system, we actually have 5 compressors out in the field. We have a Toco compressor located out here, Valacupa, Signo, Basile, and Lanciano. When creating a model, you are able to enter curves for your compressors, which allow you to constrain its operation to what you would actually see in the field. And you'll notice that for all 5 of the compressors currently in this model, we have entered compressor capacity curves here, and those curves are all enabled at this time. What we're going to do now is actually create a forecast into the future for this gathering system. I've set the forecast duration for 12 months. If we're looking at immediate short-term cost-cutting measures, 1 year seems like a reasonable amount of time to investigate that over, but it is possible to change this forecast duration. If you wanted to do 5 years, you would put in 60 months in this location, for example, and you can also change the date on which you start. So I'm just going to click Future Forecast and let that run. So what's happening right now is we are calculating all our rates and pressures, beginning with the delivery point and working our way upstream. Now that we have a forecast run, I'm going to turn on a well drawdown map. Now you'll notice that another legend has appeared here, the well drawdown map, and generally we're looking for wells that are in this light orange color, which have between a 63 and a 75% drawdown. When things get much warmer or redder than that, we're maybe drawing too hard on those wells, and if we're looking into the cooler colors, we're really not optimizing the drawdown on those wells. So with this map, we're quickly able to zone in on areas where we have good drawdown, for example here in Basile, or in Toco, or even in Valacupa, and other areas where maybe the drawdown is not as optimal as it could be, like Orta and Turi. If we wanted to see how much uplift we have available, if we were to adjust the drawdown for those wells, if I wanted to see how much uplift we have available in those wells showing a lower drawdown, I could turn on the well uplift map. And you'll notice that the legend is over here to the side, and very cool colors, this cool purple here, is showing an uplift of about 7 TCM a day. And in fact, all of our wells are showing an uplift of less than 7,000 cubic meters per day, or TCM. So while we may have room to adjust our well drawdown, we may not realize a lot of uplift in many of these areas. However, in some of these areas, there's quite a large quantity of wells, and so it may turn out that improving deliverability in these areas, even with a smaller uplift available per well, the overall increase in rates may in fact be worthwhile. I'm going to turn the well drawdown map on again and move to the Forecast View tab. And you'll notice that at the start of our forecast, April of 2015, we're producing about 750 TCM. And at the end, a year later, we're producing about 650 TCM. It turns out in this field that in fact we have a contract rate for gas of 630 TCM, so we're currently delivering higher than that, and by the end of the 1-year forecast, if we make no changes, we will still be meeting that contracted rate. If we really want to start comparing cost cutting, what we'll need to do is evaluate dollars spent and revenues coming in. And in order to do that, we use the economics feature in Piper. If I open the Inputs pane, you'll notice that I'm able to put in facility costs, including capital costs, monthly operating, and variable operating costs. In this example, we're not using capital costs. We're considering them sunk and comparing the go-forward expenditures. You're also able to input the cost of building new pipelines. You can include discount and inflation rates. And you can also add pricing for oil and gas in this interface. It is important to note that all economics in Piper are run pre-tax. There are 2 main reports available to you under the economics feature, including a net present value report and a cash flow report. We're going to focus on the net present value report. And you'll notice that for each facility listed here on the left, we have the present value of revenue, present value of expenses, and net present value shown. And if we scroll down to the bottom, it's going to give us the data for the entire field. So here are the totals for the system. We're going to use that data later to compare multiple cost-cutting scenarios. What values did I use for economic evaluation? The values shown in this table are what we used for our current test case scenarios for cost-cutting measures. They may not reflect what you're using in the field, but you really can enter anything that is reasonable for your gathering system. In this case, we've put in variable operating cost for the delivery point, wells, and compressors. We've entered a gas price, and we've put in a monthly operating cost for both wells and compressors. What we're going to do next is look at several cost-cutting scenarios that we can test using Piper. And there are 4 that we're going to focus on. The first one is shutting in fields. So if we shut in wells in specific locations, do we realize a cost savings? And what impact does that have on our future forecasting? We're also going to look at centralizing compression and decommissioning some compressors in the field. We'll investigate relocating compressors, and we have 2 different scenarios that we're going to look at. And lastly, we're going to combine those 2 different relocation scenarios. If I switch back to our base case model, and we look at the well drawdown map with the possibility of shutting in wells in mind, we may focus on areas like Turi, Orta, or Miglianico. These are small spurs in the field that are not currently well drawn down, and their uplift potential is fairly low. So the question is, what will things look like if we shut in those wells? Also, if we think back to our model calibration where we uncovered an operational issue, that issue was at Turi, and it was a liquid holdup situation. With that in mind, it may give us an additional reason to shut in those areas due to liquids issues. To get an idea of how much effect that might have, we could check the node deliverability. And if we check our deliverability plot and look at how much uplift is available and how much gas rate that would result in, it may be that this is a cost-cutting measure that is reasonable in this situation. Switching now to a version of this model where we've shut in wells, you'll notice right away these large purple bubbles around the Turi wells and the Miglianico wells. And if we look at the flag layers on the far side in the property manager, you will see that they indicate shut-in fields. So in this version of the model, in this test case, we've shut in the wells located at Turi and the wells at Miglianico. And the question is, what effect does that have on the overall gathering system? Well, first and foremost, if we have a look at our forecast route and check the initial gas rate at the start of the forecast, we're producing about 710 TCM, and previously it was about 750. And by the end of the forecast, we're producing 614 approximately. Now, if we bear in mind that our contract rate is 630, then by the end of this cost-cutting scenario, we're no longer meeting our contractual obligations, and there may be certain penalties attached to that. If we follow back up the forecast to January in this case, we're still producing 630 TCM of gas. So at this point, we are meeting our contract rates. And this is where a person would want to consider maybe bringing some wells back online in order to continue meeting the contract rate at that time. If we go back to the GIS interface and have a closer look at the well drawdown map, the drawdown at most of the wells in the system has really been unaltered after shutting in these two fields. We've already run the economics, the net present value for this particular scenario, and I've collated those numbers into a table we'll use for comparisons later. If we look back to our base case scenario and have a closer look at the compressors on this occasion, we're going to consider a centralized compression scenario with two compressors being decommissioned. There are three compressors located down towards the west, Tocco, Valacupa, and Signo. And then there are another two over towards the east, Lanciano and Basile. In our centralized compression scenario, we are going to decommission the two smallest compressors in this model, which would be Signo here, as well as Lanciano here. And we're going to relocate Basile, Valacupa, and Tocco downstream near the separator and delivery point. We may expect overall to see lower rates as we will have less compression in the total gathering system. We may also expect in some areas that will no longer directly see compression, where we will actually have a change in the well drawdown. Switching now to the centralized compression scenario, we've again used flags to help us keep track of the two compressors that have been decommissioned, shown here in gray, and the three compressors in purple, which have been relocated to a centralized location just before the delivery point. Notice just how we may have anticipated at Lanciano, where we have decommissioned a compressor, we've actually got reduced well drawdown in this area. If we check the total rates over the duration of our forecast, remember for our base case scenario, we had about 750 TCM at the initial date, and by the end of the forecast, we're getting 640 from this particular scenario. Again, the economics for this have been run using the same inputs, and I've collated all of that data for comparison later. There are many ways to get data from IHS Piper, and one of those ways is to simply right-click on a facility, in this case a compressor, and I'm going to request a compressor plot. In this graph, we are looking at horsepower usage over the duration of the forecast, the gas rate declining over the course of the forecast, and the outlet pressure at the compressor. And each of these plots may be adjusted for its appearance and the axis range as required. It is possible to click on any facility within Piper and generate plots, both for performance as well as deliverability. In addition, any of these plots can be copied and taken into another software application like Excel, and you can paste either an image of the plot as well as the tabular data. Another useful diagnostic tool is the pressure distribution map. If there were a pressure tolerance that you wanted to maintain within your gathering system, you could use the pressure distribution map. You'll notice that the legend here is colored to highlight kPa ranges. If there were a pressure range over which you did not want to operate, you could simply color it a specific color and check for those areas within the model. So far, we have looked at two cost-cutting scenarios. The first was shutting in wells, and the second one is centralizing compression and decommissioning two compressors. We're now going to consider relocating the compressors that we have in the field to possibly more optimal locations. I've switched back to our base case, our original model condition. We have our 5 compressors, Tocco, Vallecupa, Signo, Basile, and Lanciano. With the well drawdown map on, we can investigate areas that may be benefited by additional compression. For example, Orta, Turi, or Miglianico. We may even be able to realize greater drawdown in Lanciano depending upon where we were to locate those compressors. Switching from our base case to the next cost-cutting scenario, you'll notice that 3 locations have purple flags. These indicate that compressors have been removed in those locations. In this example, Tocco, Vallecupa, and Signo have all been moved downstream to this location, Chieti. With the well drawdown map on, indeed as expected, those wells in Orto, which had very poor drawdown, are now in that nice orange range, 63 to 75% drawdown that we're optimally looking for. And we would expect that after moving the compression downstream of them. If we go to our forecast view, we can see that our gas rate at the start of the forecast is 765 TCM, actually higher than our base case. And our end gas rate at the last date in the forecast is also higher than that seen in the base case. Again, all the economics have already been run, and I have that data to show you for comparison purposes later. Returning to our base case scenario and focusing now on the Basile and Lanciano compressors, if we have a look at wells that might benefit from additional compression, the Miglianico area here in green with a drawdown of less than 50% comes to mind. Switching from our base case model to the next cost-cutting scenario, what we've done is taken the compressors at Basile and Lanciano and simply moved them to this new location, Miglianico, where they also affect these wells. And again, we've noticed that the well drawdown has improved from under 50% to between 63 and 75%, which is the range that we're looking for. If we check the overall forecast view and look at our gas rates, again, we're noticing an uplift compared to that seen in the base case, both at the start of the forecast and at the end of it. I'm going to return back to the base case scenario, and we're going to check one more possible cost-cutting measure. We've evaluated moving these 3 compressors to a location further downstream as well as these two compressors to a location further downstream, and both have realized an improvement in well drawdown. And we're going to have a look at what the effect would be of combining those two relocation scenarios. If I switch to that scenario, notice that in light purple, those are the three compressors that we have moved to this new Chieti location, as well as the other two compressors that have been relocated to the Miglianico location. And you'll notice that our well drawdown in all of these regions is in that light orange zone where we would like it to be. If we check our overall gas rates, we are about 25 TCM higher than in our base case. And again, our final date gas rate is also significantly higher. Now that we have tested 5 different cost-cutting scenarios, we're going to compare the results. I've taken all of the data from those economic reports, particularly the net present value that we discussed, and put them all together in one place for each of the scenarios. In the first row, you'll see the base case. So this is the gas field with no changes made. We're showing our present value of revenues in the first column and our expenses as a delta from the base case in the second column. What does this mean? If we have a negative value, that means our expenses are lower than they were in the base case. Notice that for all the scenarios tested, each cost-cutting measure has in fact resulted in decreased costs. The largest cost cutting happened when we shut in the smaller fields, and we have some more moderate as well as some smaller expense reductions in different scenarios. If we then look at the net present value delta from base case, a negative value implies that the net present value in that scenario is lower than that seen in the base case, which of course is what we would expect when we shut in wells, as they are producing lower rates from the field at that point in time. Positive values indicate that the net present value in this cost-cutting scenario is actually higher than it would be in the base case by the end of the forecast, and that is the case for all 3 of the compressor relocation scenarios. If cost cutting is the main driver of scenario testing, in this case, the best solution would be to shut in the smaller fields. If we then have a look at the actual gas delivery rates within the field under each scenario, the decision becomes a little more complicated. If we remember that the delivery contract amount is 630 TCM, and we check how much our year-end gas rate for each scenario differs from that contracted gas rate, we arrive at the numbers within this column, the delta from contract. In our base case, we were already delivering about 19 TCM greater than was required by our contract. In the cost-cutting scenario of shutting in smaller fields, we're actually below the contract, and that happened in about January of that year with a few months left in the forecast, so we're not honoring our contract in that case. For all other scenarios tested, we are still exceeding the 630 TCM contract rate by the end of the forecast period. And note that in the final cost-cutting scenario, where we relocated all 5 compressors downstream, we realized almost 40 TCM increase in the gas rate by the end of the forecast. So under all the scenarios, with the exception of shutting in wells, we're still able to honor our contract at the end of a 1-year forecast term. Another interesting consideration is that you may want to consider selecting a cost-cutting scenario that comes closest to meeting the current contract delivery rate without actually exceeding it. Doing so would allow you to capitalize on higher commodity prices at a later date. After reviewing each of those scenarios, as well as their cost-cutting results in both rate and economics, What scenario would you choose? You would need to go back and consider that you need to maintain a minimum production rate in order to meet your contracts. You would need to consider what costs are being directly incurred and what costs are indirectly incurred. So for example, we haven't included the cost of relocating compressors in these examples. And you also need to keep in mind any lost revenues that are realized during any scenario modifications. After doing all of that, then you want to determine the best option on a go-forward basis. Shutting in wells did yield the largest cost savings, but it did not meet the contract delivery rates. So you would need to look at either the cost incurred by not meeting that contractual obligation or start bringing wells back online. Relocating all 5 compressors had the largest increase in gas delivery rate and the largest net present value, as well as the 3rd highest cost savings, so that may be a scenario worth further investigation. In summary, IHS Piper can help operators identify operational issues, including bottlenecks and liquid buildup, amongst others. Potential corrective measures can be tested in the software in multiple scenarios, and field cost-cutting measures can also be quantified and their future impact modeled. Scenarios to increase revenues can be evaluated, including any capital and operating spending, to evaluate overall profitability of each scenario. The corresponding rates and economics for scenarios can be easily output from the software and used for future planning. You can quickly test multiple solutions or optimization options and compare the results for each without any infrastructure expenditure. Scenario testing is simple and easily accomplished. As a result, Piper users can test many alternative field optimization scenarios and find the best possible solution for minimizing costs or maximizing profitability of an operating field. I'd like to thank you for your time today, and if there are any questions, please feel free. For those of you who didn't hear it, the question was that our models only showed gas wells and compressors, and does the software work for oil? Yes, it does. Currently, we support pumps with operational curves and rate profiles for oil wells. Analytical oil models will be supported in the next release of Piper later this year. There are also equation of state relationships that allow you to model liquid-rich dropout or gas evolving from oil, and black oil relationships are also available. The next question was, if a field is shut in, is it possible to quantify that flush production later when the field is brought back online? Yes, actually it is. If you use a Harmony RTA analytical model, increases in the near wellbore pressure are considered. So during that shut-in period, the pressure changes are considered and the corresponding flush production when wells are brought back online will be modeled. And another question? Are there detailed plots that show the pressure loss through a pipeline? Yes, there are. You can right-click on any node and generate a forecast plot, which will show you both your hydrostatic and frictional pressure losses over the course of the forecast. Can you enter economic information on a well-by-well basis? Yes, actually you can. And I'm just quickly going to pop over to Piper here. Under the forecast options, if you select working interest tracking, you can put in the number of companies that you have, change the names if necessary. And then if you go into any facility editor, you can actually put in the working interest for each company. So you'll notice here you're able to put in the capital cost, variable costs, and fixed costs on a well-by-well basis, and then it will take into account your working interest and do the calculations accordingly. And maybe one more question. So if you do not have location data for your field, can you still build a model? Yes, you can. You can actually use Cartesian mode in Piper and quickly create a gathering system by drawing things on the screen. And again, if I just quickly switch back to Piper, I'm going to create a new file in Cartesian mode. And you'll notice there's a delivery point already on screen. I would be able to add compressors, add wells, grab links, and just connect up my system as required. Well, thank you very much for taking the time today. I appreciate it very much. If you have any additional questions, please feel free to send them to me. Thank you.